Moving through potential difference. In the figure, a dust particle with mass m equals 5.0 times 10 to the negative 9 kilograms, which is equal to 5.0 micrograms, and a charge, q naught equals 2.0 nanocoulombs, starts from rest and moves in a straight line from point A to point B. So for the identifying setup, we're just going to want to write down some of our equations. And before we get there, let's just quickly mention what's going on in the picture. Here we have our dust particle, and it's traveling from this point to this point, and it has a positive charge, so that does make sense that it's going to be traveling to the right. It's going to be attracted to the negative charge and repelled by this positive charge. So we're going to have conserved mechanical energy because the only force acting on this particle is the electric force, which is a conservative force. And since mechanical energy is conserved, we can say that the kinetic plus potential energy at point A is equal to the kinetic plus potential energy at point B. So the kinetic energies we should know how to calculate. The potential energies we can get from the potentials. So in general, the potential energy U is equal to Q, the charge, times the potential of that charge. So then for point A, we get U sub A equals Q naught V sub A, and then for point B, we get U sub B equals Q naught V sub B. So now to put all this into play, our kinetic energies should be somewhat obvious. At point A, the particle starts at rest, so we have 0 kinetic energy at point A. And then at point B, we have some speed, and that's the speed we're looking for. So we're going to have kinetic energy of 1/2 mv squared. So then plugging everything into our energy equation, we get 0 kinetic energy plus Q naught times VA is equal to 1/2 mv squared plus Q naught times VB. So then to solve for V, what we would do is subtract by Q naught VB, multiply both sides by 2, divide by m, and then finally take the square root, and we would end up with V equals the square root of 2Q naught times VA minus VB over m. So then continuing our calculation, we need to figure out what VA and VB are. Since we know the electric field is being caused by point charges, we should also know that the potential due to those fields is V equals Q over 4 pi epsilon naught times R, where Q in this case is the charge of the particle creating the electric field. So then for VA, when we plug everything in, we get 9 times 10 to the 9 newtons meters squared per coulomb squared. And this number comes from this bit right here, 4 pi epsilon naught, where epsilon naught is a given constant. And then we get 3.0 times 10 to the negative 9 coulombs over 0.01 meters plus negative 3.0 times 10 to the 9 coulombs over 0.02 meters. So then what we're doing here is at point A, we're figuring out the potential caused by the 3 nanocoulomb charge, and then figuring out the potential caused by the negative 3 nanocoulomb charge, and then adding them together. So in this first part, it was a positive 3 because that one's only 1 centimeter away from the dust particle, or 0.01 meters away. And then the negative charge is 2 centimeters away. So that's why it's negative 3.0 times 10 to the negative 9 coulombs over 0.02 meters. So then after a careful calculation, we should get that the potential at A for the dust particle is 1,350 volts. Now VB is going to be very similar. We're going to plug this in again, which is 1 over 4 pi epsilon naught, comes out to 9 times 10 to the 9 newtons meters squared per coulomb squared. And now this time, the positive charge is 2 centimeters away, and the negative charge is 1 centimeter away. As you might be able to imagine, the calculation is going to be very, very similar. We're just going to get a slightly different result. And the different result is that the potential at B is negative 1,350 volts. So I'm going to do VA minus VB separately because it's an easy thing to mix up when you're working with such bizarre numbers. So if we do VA minus VB, we get 1350 minus negative 1350. So they don't actually subtract, they add up. So the difference of the potentials is 2,700 volts. And now when we get to do our actual calculation, we can plug everything in. So from this equation onto this equation, we get 2 times Q naught, which was 2 times 10 to the negative 9 coulombs, times the difference of the voltage, which is 2,700 volts, all divided by the mass of the dust particle, which is 5 times 10 to the 9 kilograms. And after carefully calculating this, we end up with 46 meters per second, which is pretty crazy because dust particle starts at rest, and then within 1 centimeter, it's now traveling at 46 meters per second. So that's a crazy acceleration. And then for the evaluation, we should keep in mind how weird this problem is, but also that it does make sense. This dust particle having a positive charge is going to be pushed to the right by the positive charge, and then pulled to the right by the negative charge. So both charges are contributing to this dust particle's speed, hence the large speed after 1 centimeter. And finally, it's worth checking to make sure our units make sense. You should know, or now remember, that 1 volt is equal to 1 joule per coulomb. So then if we came back up here, if we had joules over coulombs here, coulombs would cancel out, and then we would have joules. And then joules divided by mass gives us meters squared per second squared, but then we take the square root of that to get meters per second.